Anyway, he's got some interesting products that kind of captured my attention. You know, you think about how great ForeFlight has been, and the information that you can get on ForeFlight that, you know, 20 years ago was unimaginable. Well, he's got a couple of cool devices that he's going to tell us about.
Thanks for the intro, and sorry for making your break a little early there. I was flying all day and had to step outside and get some cold air, otherwise I couldn't fall asleep back there. So I'm here to talk about LIDAR and radar altimeters today. I'm Sean Skeeter, Sherman Skeeter Enterprises, and my company, Skeeter Enterprises, makes LIDAR and radar altimeter for general aviation aircraft. So,
Is it on? Make sure it's turned on.
We're in the right state for skiers.
that works better. Okay, so my background, I'm a mechanical engineer, graduated at University of North Dakota. After I did ROTC there, I did 4 years as a developmental engineer in the Air Force Research Labs, working on cool technologies there. And then in 2019, I started my company, Skeeter Enterprises. So we got a high school chemistry lecture earlier today. Now we're going to do the high school physics lecture right now. So, big difference when we're talking LIDAR versus radar. They're both on the electromagnetic spectrum. The only difference is the size of the wavelength or the frequency. So radar here you see is 24 gigahertz. LIDAR is a significantly faster frequency at 331 terahertz. Typically, when you're talking radar versus LIDAR, you're not going to use the same units. So radars, anything in the radio wavelength, you're going to use the frequency here. In visible wavelength and infrared, you're actually going to use the wavelength. So it can be a little confusing to distinguish these two, but these are important numbers because this is going to tell you exactly how it's going to work. So you can see here the radar, the wavelength is significantly longer. It's 12.5 millimeters. So you can, that 12.5 millimeters, that's just a little over a centimeter. You can actually see that. Versus 905 nanometers, that's pretty damn small. You're not going to be able to see that kind of wavelength there. So we're talking 24 gigahertz for the radar, 905 nanometers for the LIDAR. And the next slide here, a lot of the radars are going to have multiple different frequencies associated with them. So it's important to distinguish these when you're talking about them. So some of these radars are operating at 77 gigahertz. That's the actual frequency on the electromagnetic spectrum that they're operating at. But with those frequencies, they'll also tell you the sample frequency. So these can look the same, but they are not interchangeable. And just giving you some background here. So when you do go out and buy one of these, or you're looking at these, to make sure that you're looking at the right frequencies here. So this is the actual operating frequency, 77 gigahertz. Sample frequency is 1,000 hertz. So 1,000 times a second, it's taking that measurement. And then the bandwidth is how much of the frequency it's taking up. So it's taking up 1,000 megahertz of this center frequency. So it operates from 76.5 to 77.5 on that center frequency. So this can be a little confusing. I'm sure I just made it even more confusing for you. But something to keep in mind when you're looking at these radars. So they operate mostly on the same principle, which is time of flight. So radar, LIDAR, what you're doing is you're sending photons down the ground and you're measuring how quickly these radio or LIDAR waves come back, and you can measure that and you can get a pretty accurate measurement as to how high above the ground you are. This is fairly basic technology. So for instance, the formula is real simple. Distance is just times the time of flight times the speed of light. So at 100 feet, it takes a lot of zeros after the decimal point before you get that reading. But the electronics are so good that it's fairly easy to measure that, and you can get extremely accurate measurements here. So why would you choose radar versus LIDAR? How do you make these choices? That's the biggest question here. So radar is just not going to be as accurate. So if we go back, radar is inherently going to use a longer wavelength. Because it's going to use that longer wavelength, it is inherently going to be less accurate than LIDAR. The shorter the wavelength, the more accurate your instrumentation can be. So LIDAR is really easy to use. That's why it's used so often in measurements. But as we'll see, there are some downsides to the LIDAR. So the LIDAR is going to be more efficient, more energy efficient, because you can get that little short wavelength there. The biggest problem is that LIDAR is typically not going to work well over water. And that is the biggest difference, in my opinion, between LIDAR versus radar. Radar is going to give a really good reflection over water. LIDAR over water, especially at 905 nanometer frequency, the infrared, the water will absorb 99.9% of that energy within the first couple of inches. So you're not going to get any return whatsoever. So a LIDAR says it's good for 1,000 feet. You're not going to get anything until you're 10 feet above the water. So it's, whereas the radar will still give you that good bounce back, and you'll still see 1,000 feet over the water. Other differences is that the LIDAR needs something optically clear to go through, so basically glass or plexiglass or something like that, whereas radar doesn't care if it's optically clear, but it has to be a non-conducting material, so you can't put a radar, say, on the other side of a sheet of aluminum and expect to get a good return. So you gotta be careful where you're mounting these options. This is another big difference between LIDAR and radar. So when we say something is laser focused, you know, we're using a LIDAR, it is literally laser focused. So in this example here, we use LIDARs and radars in a lot of autonomous vehicles. If you follow this LIDAR beam, it's going to give you an exact measurement right off the corner of this car, right? So if you take that LIDAR and you measure this distance, you'll know exactly how far it is to this particular corner of the car, because it's quite literally laser focused. Problem with radar is this beam divergence angle. Now LIDAR has beam divergence angle too, but it's so small that it's really not much to take into account for, whereas radars, especially modern FMCW radars, can have quite a large radar cone here. So if this radar is coming out, it's measuring this side of the car, this corner of the car, and it's measuring the car next to it. So when it gets this radar beam bounced back, it's trying to take all these measurements into account. And depending on the software here, it might be trying to average them, it might be trying to differentiate them. But this is something that is inherently different between the LIDARs and the radars, is this beam divergence angle. And this can be important when you're mounting these on aircraft if you're going over trees, for instance. You know, that LIDAR is going to measure the distance to the leaf underneath it, right? If you are bouncing over leaves on the trees, it's going to tell you the difference between one leaf and the other. Whereas the radar is going to tell you probably the average between the heights of the tops of the trees. So it's going to be a little bit different measurement theory behind these two technologies. And so this is a really good point of reference for how little red light penetrates the water. So this is something they teach in dive school. You can see right here at the surface, the red's very vibrant, and as is this blue. But if you get down 100 feet, the red is completely washed out. This item is now black. It's because the red light isn't penetrating the water at all, versus the blues are still getting down here. And this is an interesting concept that some companies will use for measurements, particularly bathymetric measurements of lakes and rivers and stuff. They will deliberately use a green laser to measure the bottom of where the water is. And I cannot remember which company it is. I want to say Whip-Air, but I can't swear to it. They actually use two different colored lasers for their gear announcement system. So one will be infrared and one will be green. And so what the computer is looking for is, okay, if they're both bouncing back to me and reading the same distance, I'm over land. If only green is coming back, or that there's a large difference between the two, now I'm probably over water, and let the pilot know that. And so that's a clever way to get around the, gear check problem on amphibs and seaplanes. It's not perfect, but it's better than nothing else. So So my product, Stadia, I make LIDAR and radar altimeters, and I'm just going to give a quick demonstration of how my product works, so you know in general when you're getting a radar or LIDAR altimeter what you're looking for. So like I said, they're typically going to be LIDAR or radar. Connection to the pilot can be various ways, but a lot of them are going to be Bluetooth to an app. And so it's going to Bluetooth to an app on your phone. Typically, you know, you've got your Bose or David Clark's plugged into your headset there, or plugged into your phone so you can get audio cues. That's the big thing that they're looking for, because you don't want to be looking at your phone when you're coming for landing. You want to be getting audio cues just like the big guys do, right? Let you know, okay, 50 feet, 40 feet down to the deck. The difference is with new LIDAR and radars versus the old radars that are on like typical Boeing 737s. I was showing that the accuracy is plus or minus 8 inches on these new radars versus the big guys can be plus or minus 10 feet. So the new radars and LIDARs are significantly more accurate than the old radars that were essentially unchanged from the 60s and 70s. So pretty simple, you can go through, calibrate the system to your wheel height, because when you strap this on your wing or your strut or something, you don't care how high the device is to the ground, you care about your wheel height above ground. So there's typically going to be some sort of calibration function built in, and then you can set settings on here, you know, at what altitude you want to start hearing alerts, what kind of alerts do you want to hear, and then there's an operational screen, you know, if you want to turn the radar or LIDAR in standby or active mode because you don't always want to hear it, a little display to make sure everything's working correctly, etc. Get the video right? Yep. So in this next scene here, we're going to see a LIDAR in operation on a Cub here, and then in the center here you're going to see some very, very blurry numbers. And then on the right-hand side, you see the actual Stadia in operation on the wing strut, and then there will probably be some piercing noise letting you know how high above the ground the aircraft is. That's it. All right, so that's a quick example of one of the audio cues that you can get. So as the pilot was descending towards the ground, you could hear those audio cues getting shorter in duration and higher in frequency until the pilot's right on the deck, and then it goes to a solid tone. When I was in the Air Force, we were doing some similar experiments with other technologies in terms of how to get this kind of information to the pilot. And what we found was that while the voice works well, the tones work significantly better because the pilot doesn't have to think about it. There's quite literally less processing that has to go on in the pilot's skull to get this kind of information. So when you're trying to get little discrete packets of information to the pilot, it turns out that tones are the best way to do it. Now, a lot of pilots, you know, especially the big rig pilots, they still want their audio cues from the bitch and Betty, and so that's always an option. But I always tell pilots, you know, the Air Force data is pretty clear on this. If you want this information to help out in the quickest path possible, the tones are usually the way to go. All right, I'll just, no, that's not gonna work either. Okay. All right, so on my particular setups, like I said, I have the two types, the LIDAR and the radar. The LIDAR has about 130 feet of range versus the radar has about 300 feet of range. They're both portable and self-contained, so they have rechargeable lithium-ion batteries. And so get about 12 hours of endurance. What I like to tell pilots is that'll last a lot longer than your fuel tanks or your bladder will. Additionally, obviously, the Stadia Neptune, it was developed later after this LIDAR version, but the LIDAR version wasn't water capable, and so it was pretty clear that the seaplane pilots were suffering from the glass water landings. And so I made a water capable version by swapping out the LIDAR with the radar. So my particular state attachment points a couple different options. So there's a strut-based option that you saw in the previous video, and then there's also a tie-down ring option for a lot of the low-wing pilots are really appreciative of having some sort of AGL height awareness, because those low wings, you know, they get out in your peripheral. And if you're landing at your home base, you don't really need it, right? But if, you know, if it's a low light situation or maybe your peripherals aren't as good as they used to be, it can be really handy to have some out there to really help you nail that landing. Not that any of us would come in for a hard landing, of course. And then there's also experimental versions, so if you're flying an experimental, I mean, you can slap this thing just about anywhere. The hardware is extremely user-friendly for mounting. So, why do you need this? I mean, we just saw, you know, we were talking to the NTSB person, you know, these hard landings will creep out and grab you. So, low light conditions, I mean, we've all seen something like this, you know, you're out there in the snow, low light conditions, flat light, and you just can't tell where the horizon is anymore. And while ideally we don't have to land into this stuff, sometimes the ideal circumstances don't agree with what we have to do. And so that's what you gotta do. And unfortunately, this pilot found out the hard way, and what's ironic is, this is a commercial helicopter. By law, they have to have one of those old style radals on that airframe. And the problem with those old style radals is they're using a really long wavelength, and like I said, it's good for plus or minus about 10 feet. And in the snowpack, that long wavelength doesn't give a very good reflection. So those old style radals really don't work that well in this type of condition. Whereas the shorter wavelengths, like 24 gigahertz, or the LIDARs, the 905 nanometer wavelengths, those work significantly better in these conditions. Unfortunately, the FAA mandates that these guys are using 4 gigahertz wavelength or frequency, and unfortunately it leads to some terrible accidents. Glass water landings, which is what most of us here are concerned about. I mean, we've all seen this. You come in and you can be 5 feet above that water, you can be 50 feet above that water. And you know, there's techniques for getting into these things, obviously, but if you're coming into a short lake and you need to get in there, and it's glassy water, it's bare. And so that's where having a radar altimeter, in my opinion, is probably the best option, because if you're coming into your home airport, your home lake, and you got a little chop on the surface, you don't need a radar altimeter. I hope you don't. Otherwise, maybe you need different lessons. But that's not always the case, right? Maybe you're coming in somewhere you're unfamiliar with. There's absolutely no reference points here in glassy water. You're running low on fuel or something. Now you want that radar. Now you're really wishing you had something like that. These radar and LIDAR altimeters, they're not for all the time, but they are there for those times where you need a little extra help, or that little extra help is gonna turn this from a, oh shit landing to, you know, that wasn't too bad. Poor field of view, obviously, like I was talking about the low wing materials, and then you can tell I built this slide deck for people in the lower 48 because I completely don't have to mention bush flying in this community here. But the training aspect is also a nice one for having radar and LIDAR altimeters. I sell these Stadia altimeters to several flight schools, and what the training folks will tell me is they don't want it to become a crutch. Instead, what they will do is they will have the student fly down the entire length of the runway at exactly 3 feet. And they know it's exactly 3 feet because the LIDAR is telling them you are at 3.0 feet. They'll have the student fly the entire length of the runway at exactly 3 feet. And it's really good for building that pilot's sense of vision of how high above the ground they are. Then they come back around, turn the LIDAR off, and now the student is looking out, but they know exactly what 3 feet looks like, instead of guessing, oh, maybe I'm at 8 feet, and they come in for a flare and break the landing gear a little bit. So the training aspect is really valuable in terms of using these LIDAR and radar altimeters. But this is the biggest reason to use it. The number one cause of aircraft accidents is pilot error, hands down by the widest margins. And additionally, 64%, 2/3 of student solo accidents occur during the landing phase. So clearly, the landing phases are what's causing the vast majority of accidents. These hard landings are causing, you know, a good portion of them. Bending those landing gears, bringing them in, and it gets expensive at the least end of the scale, and at the worst end of the scale, it's killing people. And every time I give this speech, I get pushback saying all these extra bells and whistles are taken away from the pilot experience. and I'm sure everyone in this room has heard the same thing from some other pilot around here before. And I always tell them the same thing. The Air Force pilots in the 70s thought the exact same thing when they were putting these things on F-16s. And not all of them, but a significant portion of the pilots were bitching, hey, you know, I don't want this thing telling me how high above the ground that I am. I don't want this thing taking control because it's going to do something I don't want it to do, and it's going to kill me. And then they put in the GPWS on all these airplanes, and there was a significant drop in terms of accidents. And so it's gotten to the point where even on real missions, the GPWS is still going to be activated, even if they're doing terrain following radar approaches, because the risk of colliding with the ground is still more significant than pretty much any enemy action that can be taken, including popping out, getting hit by a radar, and having a SAM track you. That's how important the GPWS is on a lot of these aircraft. So these pilots can bitch and moan about having all the extra bells and whistles, but at the end of the day, a lot of these bells and whistles are what's going to save pilots' airplanes and their lives. So with that said, I'm Skeeter Enterprises. I make the Stadia altimeters, and I'll be here for extra hours, so if you want to come talk to me afterwards. Are there any questions?
Are the radar altimeters affected by cell, like a 5G cell signal?
The question was if the radar altimeters are affected by 5G cell. The answer is no. So if we go back to the high school physics lecture here, what I was talking about before is that the old radals are 4.8 gigahertz. This is operating at 24 gigahertz, and this is operating at 331. The 5G networks are operating at, I want to say, 5.2 gigahertz, or somewhere around there. And so it's pretty close, and that's why all the old radals can get interference. Whereas these ones, the frequency is significantly different, and so the new radals and LIDAR altimeters will not get that 5G interference.
Thank you.
Your installation on a certified aircraft, this is a minor alteration on required safety equipment. Is that how your paperwork runs?
So the question was installing these on certified aircraft, if there's any SCCs or anything like that. The answer is no, there is no paperwork involved because it is considered a temporary attachment like a GoPro. And so because of that, you don't need any extra paperwork or anything. So as a matter of fact, on the low wing, this is quite literally a GoPro attachment, and it weighs the same as a GoPro. And on here, it simply just straps to the strut here, and so according to FAA rules, temporary attachments that don't affect the flight characteristics do not need any sort of certification or paperwork whatsoever.
Does it calculate for like the flare and also like if you have a tail wheel and it starts angling back, you know, does it increase the length that it's actually telling you have an error?
That's a good question. So the question was if the flare of the aircraft will affect the accuracy. The answer is technically yes. Doing the calculations is real quick trig. It turns out it's just a couple of inches, even on some really severe like rolls or flares. Typically what I'll tell pilots is have the aircraft in the landing configuration when you do the calibration. So if you're on a tail wheel, make sure it's sitting down the tail wheel and then calibrate it. The convenient part about the strut mounted one for Cub, you're already in the tail wheel configuration and it's basically mounted on the axis of rotation. So the difference in measurement is really small. So technically it does offset by a couple inches. In reality, it's not so much that a pilot will notice. Back.
So you were mentioning the difference in land and water. What about snow?
So the question was the difference in land and water versus snow. So that's a good question. Both will work over snow because the frequency of both is so high. That being said, the LIDAR seems to have a little better reception over the snow. If it's like if it's not very densely packed snow, sometimes the radar will have a little bit more penetration in that snow, but overall it still seems to get a pretty good bounce back off the top of the snow.
What's the cost of these systems?
So the cost of my systems, am I allowed to talk about?
Yeah.
Okay. This is not supposed to be a commercial briefing, so I just want to make sure I'm not getting in trouble here. The LIDAR systems go for $615, and the radar systems go for $1,107.
when you went to the display picture on the video that you had, so you had it just like your phone mounted, is that what, like, so when we talk about audio and visual kind of cues, so is there a color change on the, you know, coming in, like if you're, as you get lower, is the color changing on the screen that you're seeing? So are you having a visual cue as well as the audio cues?
So the question was if there is more of a visual cue besides the numbers changing on the screen, so like if there's a color cue on the screen as well. The answer is no. I deliberately didn't put that on there because my worry was I could distract the pilot from looking out the window.
Yeah.
And so all they need to do is, you know, look down for a tenth of a second and bad shit's gonna happen, they're gonna blame me. So I deliberately left that kind of.
Yeah, the reason why I asked is kind of an interesting, I'm a nurse and I have lots of history in clinical research, and one of the things that, you know, people talk about alarm fatigue and just hearing certain things. It's not a critique, it's just a question. Because sometimes we can become, you know, like we all in this room, I know,
Desensitized.
terrain, we don't listen to that. Everywhere we fly here, and most of us probably disable that because it's like constant, but it was just a question.
That's an excellent point. I'm glad you brought that up, actually. So she was talking about alarm fatigue. So you hear train in your headset, or you hear the beeping. You know, you don't want to hear that from 500 feet, because by the time you get down to the deck, you don't care anymore, right? So, where is it?
You're talking about when you set your own parameters?
Yes.
Yeah.
So you can set this to go off at whatever altitude above the ground you want, specifically to combat that. Because you don't care when you're 300 feet above the ground, right? Like, you already know that. You know, you're not about to hit the dirt yet. It's the last few feet that you really care about. And so in my system, you can set this to whatever altitude you want, so you don't get that alarm fatigue. So you don't have that chirping in your ear the whole way down. So typically, even though they're good for up to 300 feet, pilots will typically set this to only go off 15, 20 feet above the dirt. So that way you're not getting that alarm fatigue. So when you start hearing those chirps, now you know, oh, I set that for 20 feet. I know I'm 20 feet above. And now you only have 3 more changes in the tones before you're hitting the dirt or the water. So it specifically combats that alarm fatigue. Thank you for asking that question.
So we have angle of attack with the chirpy bird in it as well. Is there a distinguishing, or are you gonna have to shut one off?
So the question was if this will basically run in, if the angle of attack alarm will also be chirping at you while this is. The answer is yes, it will. My system is not set up to override any other system, I guess. It's going through your phone's audio. So depending on where your angle of attack alarm is coming through, whether it's an instrument panel or through an app on your phone, it may or may not interfere with this sound system. And that's really more of a system-by-system integration piece. So I can't speak to any specific system, but overall, you're probably going to hear both of them at the same time, I would guess. And then I would say, in my system, you can set it to have the tones, or you can have voice alerts. So you can change between the different alarm sets that you're going to hear.
So if it's voice, it should say 10, 9, 8, 7.
Exactly, yeah. So if you have the voice alarm on, it will top you down, so it gives 10-foot increments down to 10 feet, and then at 5 foot, it starts going in 1-foot increments. So it'll say 5, 4, 3, 2, 1, all the way down to the deck.
This is Bluetooth to your headset?
Yes, so whatever method you're connecting your headset to your phone, either Bluetooth or wired, that's how the audio is going to get through to your headset.
Can you adjust the tone frequency? So if you've got 2 tones that are similar, you might be able to shift this one to a deeper tone or to a higher frequency. Is that adjustment in the app, or is that something not in the app?
So the question was if the tones can be adjusted frequency in the app. The answer is, in my case, no, they cannot. So it's already set in stone for there. But like I said, you can change to a voice tone if you want instead. Anyone else?
Can you move between planes easily?
Yes, it's extremely easy to move between planes, and I kind of shot myself in the foot with that because the training schools will have 50 airplanes and they'll only buy 3 of these things from me. So. Let me see if I can find the picture here. But yeah, so you can see here the straps that connect this to the strut. Obviously, these come off really easy. This is just a simple pressure clamp on the tie-down ring. This clamp is made by My Pilot Pro. He does really good work. But this is really easy to take out. There's no tools involved for mounting these. And so afterwards I can show you, but this is the unit right here. It's got a couple of buckles, and so it comes off real easy. And in addition, it also has a bayonet mount, so it can be moved between different mounting features as well. But yeah, it's very easy to move between aircraft. I will sell you multiple though, just in case you're wondering.
I wish you rented them
That is something I thought about.
for students.
Right. Anyone else?
If you do have multiple aircraft, can you set up a different profile for each one in the app to adjust the height? So if you like go back to the screen where you,
Right, so the question is, if you buy one of these to do multiple aircraft, can you set it up for each individual aircraft when you're mounting it? Question is, sort of. The calibration is super simple. So all you do is you turn it on, you press calibrate, and it's automatically calibrated to the aircraft. And it's as dirt simple as possible. The easier option would be to buy multiple of these.
thank you.
Any other questions? All right, thank you so much, really appreciate it.